So, so welcome back. So we are very happy to have Professor Abramovich for his second lectures on resolution for everyone. So,
thank you very much. Can everybody hear me, please? Okay, so this is where we arrived. I stated a theorem, and I'll focus on this theorem. Or I can use this. So I'll focus on this theorem, which says that if I use the weighted blow-up that I told you how, you are sure you won't fall asleep this way? I told you how to define the invariant. I told you how to define the center. And the theorem says that if you use the weighted blow-up, which I told you how to perform, then the invariant will immediately drop. So this is what we saw always holds for usual blow-ups for curves. There's an invariant that drops. We saw that it's not so easy if you use usual blow-ups for surfaces. But I now say that in general, the method that birational geometers have been using a long time of weighted blow-ups, if you do it stack theoretically, it will immediately improve the singularities. So what birational geometers have always loved actually works in general. And it gives you what birational geometers always want, namely a resolution of singularities. So that's what this theorem says. So if you pull back the ideal, there'll be an amount of exceptional divisor that you can pull out of the resulting ideal, of the pullback ideal. The rest is what we sometimes call the weak transform or the good transform. Strict transform is a bit stricter in general, but already if you just pull back an exceptional divisor, you don't erase other stuff that might still lie inside the exceptional. It's still the case that the new ideal will have a better singularity. So people asked me before, so my goal for this lecture, so we basically covered everything. I told you what you need to do, and here's the main result, and everybody's happy. My goal today is to first give you a few examples. People ask me to do some things explicitly, and to give some proofs of some nice pieces of I have a long list. I'm not going to finish everything in an hour and a half. Okay. So let's try to do it. And so the first thing I was asked to do was this is my list again, was to calculate an example of the coefficient ideal. So here's our familiar and beloved Whitney umbrella. Sometimes I write plus, sometimes I write minus. I hope you don't mind. It's the same singularity after all. The order, as we know, is 2 because we see that there's an x squared there. And if we take the derivative with respect to x twice, we'll get a unit. Here I wrote the derivative ideal. And I already noticed that you don't need to include the elements of the ideal itself because, at least in characteristic 0, you can always multiply by x and then take a derivative by x, and as part of the deal, you'll get the original function. Okay, so I just took derivatives. Derivative. What am I saying? Sorry. No, it's good to take to be efficient. So you take the derivative with respect to x, the derivative with respect to y. If you want to do other things, you need to take other elements of the ideal, and derive them, but I'll just put in what is left from. Okay, so this you don't need because x is in there and yz. Oh, so this is y squared z. That's what I'm confusing myself. So one issue with resolution of singularities is you always get the computations wrong. You have to do it twice. Okay, so you want to notice at least that this is the important part. This is generated by that. X will kill this, and 2yz will kill this. I mean, you don't need a 2 either. I just kept it because I wanted to compute. Okay, so this is the derivative. And of course, the second derivative will have a unit. So at least in characteristic, different from 2. An exercise for you to see what happens in characteristic 2. It's a very interesting example. Maybe we'll get to it at the end. Maybe we'll get to it at the end of the conference. I don't know. Okay, so we know how to resolve this in characteristic 2. But okay, so let's do this in characteristic 0. And people ask me how to compute the coefficient ideal. Since the order is 2, I will always compute the coefficient ideal with respect to the order. In various papers, you'll see that it's sometimes useful to do other things, but we don't need other orders here. So we need to put together monomials of weighted degree at least 2 factorial. The order of the ideal itself comes in degree 2. The derivative is in degree 1. So I need to take combinations of monomials of degree at least 2. So I need to take the ideal itself in degree, so to the power 1, that's already degree 2. That gives me a 2. If I take the derivative ideal, it's only degree 1, so I need to take it squared. So this, again, is degree 2. So let's compute this. So this is, and then I need to take all products of elements from here. So I'll put here of 2 elements. So x squared, xyz. You notice I crossed out the 2 because in characteristic 0 I can. Y squared, z squared. But notice I don't need y squared, z squared because with the x squared, I kill the x squared here and I have y squared z. I should, what am I missing? xy squared. Right, so you need to take all products of 2 elements from D of I. And of course, again, you don't need this because it's already generated. Did I put y to the 4th? I should put y to the 4th. Y cubed z I don't need. Y to the 4th I do need. And in fact, that's all you need for this computation. One thing that we do use in the forward computations of invariants is we restrict this coefficient ideal to the vanishing locus of x, because x is a maximal contact. So I2 is this modulo x, and modulo x you have y squared z, and y squared z squared you don't need. And I think the only thing left is y to the 4th. Right? Jarek, am I missing something? Or is that? Yeah. Right. So the next step would be to compute a maximal contact element for this ideal. What's that? Is generated by y squared z. So I already crossed out some things that are already generated by what I wrote. And hopefully I didn't forget anything. Usually I do forget something, so please check. All right. So the next thing we need to do is to calculate the degree of this. The degree of this is 3, and find maximal contact elements for this. And in this case, we have both y and z are maximal contact elements in degree 3. So so there are some secrets in the art of resolution of singularities. And one secret says that if you have 2 different parameters, two maximal contacts that together are part of a regular sequence, you can take them both together and not have to do a coefficient ideal again. So the complete sequence of maximal contact elements are X, Y, and Z in the sequence of events, X appeared in degree 2, Y appeared in degree 3, and Z appeared in degree 3 as well. Okay, so that's one computation. And as we have seen, when we blow up this, we immediately get rid of one singularity.
Can you say again 2, 3, 3, where they come from? X squared.
So 2 is the order of the original ideal. 3, 3 is because the order of this ideal is 3, and you are supposed to rescale it. So in fact, you need, so 3 actually happens to be equal to 3 over 2 minus 1 factorial. So order 2, ideals of order 2, the first step is rather easy. I'll give you in a minute another example where you have to rescale. So in this case, you don't need to rescale the 3, 3 by the factorial of A1 minus 1. So have I answered your question? Okay. Let's do another example because I was asked to do an example that shows something a bit more meaningful. And I computed it ahead of time and hopefully correctly. So I'll take the ideal x cubed plus xy to the 4th. I think the picture of the singularity is this. It's 3 branches meeting at the origin and tangent to each other. Okay. So x equals 0 is the vertical line, and then you have the other factor x squared plus y to the 4, which up to multiplying by I is 2 parabolas looking like this. Okay, I mean, we cannot draw things over the complex numbers, but we can pretend that we can. Okay, the order of this is of course 3. So we need to take the first derivative. I wrote here the first derivative ideal. Taking the x derivative gives you this. Taking the y derivative gives you this. Then I took the second derivative. And I know that the third derivative will have a unit. And I wrote here some things that appear in the coefficient ideal. So I squared. So I is in degree 3. I need to take things in degree at least 3 factorial. 3 factorial is 6. So I need to take something of degree 3 and square it to get degree 3. Or I can take I times d of I times d squared of I. I could also take I times d of I squared. That's, you know, might as well do everything. But that turns out not to be relevant for the further computation. I should put a d of I cubed plus d squared of I to the power 6, and all other monomials of weighted degree at least 6. At least 6, but you only need to take so many. The important thing so that I said I'll give you some secrets of the art. One secret of the art is that we are taking derivatives, and then in the process we restrict to x equals 0. It turns out that for computational purposes, if you don't need to prove that something is factorial or anything like that, it's enough to just take derivative with respect to your chosen maximal contact, because you're only looking for coefficients of the original equations with respect to the maximal contact. That's basically the goal of this, but to prove things factorially, you're taking all derivatives. So, I mean, taking derivatives with respect to y in some sense was a waste of time. It was not a waste of time theoretically, but a waste of time computationally. After saying that, what do we need? We are then going to restrict to the vanishing locus of x. And so you look at all the possible monomials and ask yourself what possible things will contribute to the vanishing. Sorry, I did something wrong here. So did I do something wrong? Oh, sorry. So, right, so I modulo x is going to be 0 because every term has x. I really have to take at least one derivative to get something that is not an x. And d of I cubed, I think d of I cubed is the right term. D of I cubed will give me y to the 12. D squared of I to the power 6 will give me y to the power 18 that is already there, etc. So, right. So it seems that y appears in the grid 12, but remember, you have to take y, you have to take so the invariant. So if I'm not mistaken, this is I of 2. The invariant at the origin is well, sorry, the invariant of I of 2 so is the same as its order is 12, but you need, in order to get the invariant of the original ideal, so the invariant of the original ideal starts with 3 because the order was 3. And the next term would be which power of y I need, but I need to rescale. So I of 2 was rescaled from 3 to 6, right? And so from order 3, C of I is of weight 6. So I need to divide by 3 minus 1 factorial, which is 2, back to 3. So I need to divide this 12 by 2. So, which is sort of, I mean, if you gaze at this equation, you see that it makes sense. Okay, so the relative weights of x and y are 1 to 2, or 2 to 1 to be. Okay, so that's the invariant, and that's and the center is going to be x cubed y to the 6. Now, when I write this, one thing you want to have in mind is that this is not exactly an ideal. This is a Q ideal, which in particular is an ideal up to raising powers and dividing, and up to integral closure. So when I write when I write this term, I should include in it also x squared y to the 4th, etc. Anything that is in the integral closure of this ideal, if I want to think of it as an ideal. And now you okay. So I'm spending a lot of time on this example, but hopefully this is helpful. So now you may want to see what happens when you blow this up. So I've done the Whitney umbrella example before. Let's do this example. So let me copy it so I don't forget. Copy. Oh. Paste. And now I remember, so that my center was x cubed, x cubed y to the 6. And remember, I need to rescale it. So I only know how to blow up things where the weights, where the powers are 1 over integers. The weights are in essence the inverses of these numbers, but I want to have integer weights, so I have to rescale. So this is rescaled to x to the 1/2 y. Okay. Jarek will check that I'm doing the computation right. You're not following. You're doing another computation. Okay. So using the Cox construction description of the weighted blowup, what I want to do is I write x equals s squared x prime, and y equals s y prime. So the squared comes from the weight of x. X is of weight 2, therefore x to the 1/2. Remember, here I write things of weight 1. So x to the 1/2 is of weight 1. Y is of weight 1. So these are the weights of S. In Yarek's notation, S is T inverse. But we like to argue, as I said, so we have different notations. Okay, so let's plug this in. And okay, so you see immediately that you'll have an S to the 6 coming out. Maybe I should have it in a different color. And x prime cubed. I have here x prime, which gives me s squared, and y prime to the 4, which gives me s to the 4. That's why I have s to the 6 out there. It's the same equation. So whenever you have something weighted homogeneous, when there are no higher order terms, you seem to have the same equation, but now without. So when we do the blow up, so what you see here is the transformed equation on the deformation to the normal cone. In the deformation to the normal cone, you remove x prime equals y prime equals 0, and then mod out by c star. So now without v of x prime y prime, which was precisely the singular point in the picture here. So if you want to draw the picture in the deformation to the normal cone, in the deformation to the normal cone, yeah, it was green, right? So the fact that you got the same equation means that the deformation of the normal cone of the vanishing locus of the ideal looks exactly the same. There's no other terms that sort of got rescaled. And the center x prime equals y prime equals 0 is the origin. The one thing you want to notice that will come up is that the invariant that you have here remains the same as the invariant here. Here it's actually exactly the same ideal. So it's but if you added here higher order term, the higher order terms would become would be multiplied by a power of s here. So they would be less less influential here, but the leading term will remain the same. So the singularity will in essence remain the same on the deformation to the normal cone. That's what deformation to the normal cone do for you. They give you something linear on which a singularity is roughly the same. And then you remove the red part and mod out by C star, and what you get is your favorite desingularization. So in one step, we desingularized this scheme. If we blow up once more, we principalized the equation. So these are two examples that I carried in detail. Let me know if you have questions. Yes. Yes. So the process, right. So of course, not all equations can be made homogeneous. So what the process does is maybe I'll get to it later on. What the process does, it focuses on the most important part that is homogeneous with respect to a certain valuation. The valuation is the valuation associated to the center. So in one step, you choose a center, you locate your invariants, and you isolate the leading term with respect to the best valuation that fits this equation. that leading term will be homogeneous, but there will be other terms. And the process of what will happen with other term, if you have another term here, the other term here will come with a factor of S. So it will actually be of higher order. So it will be less important once you go to the normal cone. Okay, more questions. In a sense, this is all things that we have learned before. We all knew that weighted blobs are the right way to resolve, for instance, threefold terminal singularities. So I stated the theorem and I gave you an example that invariant drops. Okay, I have on my list to start proving some nice things. So, okay, so let's go to prove. For some reason, I decided to prove. So to deal with functoriality. So remember, I said that the important aspect of the process is that it is functorial. So some aspect of functoriality I gave you in the exercises. Taking derivatives is functorial for smooth morphisms. Finding a maximal contact is functorial for smooth morphisms. Computing the coefficient ideal is functorial for smooth morphisms. And therefore, the invariant and the center are functorial for smooth morphisms. So things come out because smooth morphisms are insensitive to taking derivatives. The derivatives that you started below will still remain upstairs and behave in the same way. But there are other aspects of functoriality. So this is page 55, and I'd better follow my notes. If you prepare too much, you forget what you prepared, right? Okay. Okay, so this is what I just said. Derivative on y, lift to derivative on y1, and therefore the order of the pullback ideal is the same as the order of the original ideal at the corresponding points. If I have an element which is here a maximal contact, I should have said, yeah, an element here, then its pullback is an element in the a minus first derivative of I1. And if it were maximal contact, if it has a next derivative, which is a unit, then the pullback will also have that property. The pullback of the coefficient ideal is a coefficient ideal. And therefore, when you restrict to the vanishing locus of X, and therefore, by induction, the invariants correspond and the centers correspond. So when you do the concatenation, so remember the invariant is obtained by restricting the coefficient ideal, calculating invariant, rescaling, and concatenating. And similarly with the center. So everything was functorial. There are a couple of things that were not functorial. So one thing was the choice of X. And there's one little step that was a big transformative change, for, at least for me, for understanding resolution of singularities, and that's Yarek's functoriality argument. Wait, but this I will show you after I do something else. So first, let me show you that functoriality implies that you can glue together a principalization of different patches. So suppose Y is a union of two open sets. So Y is the smooth smooth ambient space on which I'm trying to principalize an ideal. And I write it as a union of two open sets. And I write the intersection as Y1, 2. And I say, I think I need to make sure that there's no sound here. Okay. and say the maximum invariant of I is this. And it has a corresponding center J1 on Y1 and J2 on Y2. Functoriality told me that if I restrict J1 to Y12, I get the same center as I would compute it on Y12, and similarly for J2. So functoriality says that they are equal. The restrictions are equal, and therefore you can glue them together. And because you can glue together the centers, the blowups can be glued together as one. After all, the blowup is a proj, which is a local, so it's a globalization of a local construction, so everything works. So that's functoriality implies gluing. I want to also say that functoriality implies something that we all want. When you have an action of a group on your variety and you want to principalize an ideal that is invariant under the group action, then the principalization should still have a group action. So say G acts on Y, preserving I, and J is the center associated to I. We have two maps of G cross Y. What's it in action? It's two maps from G cross Y to Y. One is the projection and one is the action, G comma Y mapping to GY. So one is the action, one is the projection. And the other thing that we know, because is that the I is preserved by G, that the projection pullback of I is the action pullback of I. That's what being preserved means. Also, we are in characteristic 0. Groups in characteristic 0 are smooth. So each one of these maps is a smooth map. And since our process is functorial for smooth maps, where am I? These two centers are the same. So the action lifts to the blow up Y1. Okay, so G still acts on Y1, which is the blow up. Should I tell you about the re-embedding process? How far am I? Maybe I'll postpone the re-embedding principle. It's a very similar idea to prove that the re-embedding principle applies. Let me go to so I wanted to say something about Wodachik's functoriality, which is here. So remember, I almost had independent functoriality, except that I chose my maximal contact to begin with. And I need to show that things are independent of the maximal contact. And here's the centerpiece of why things are independent of the maximal contact. There are other words that you have to say during the proof, which I will not dwell on, but this is the centerpiece. And the centerpiece is the following. So first, a definition. So suppose that the order of the ideal point is A, and you define the associated maximal contact ideal to be the ideal from which you choose the maximal contact elements, namely the A minus first derivative of the ideal. Does this make sense? The maximal contact element will be chosen from the previous derivative, the derivative one less than the order. And here's a definition that is due to Kolar. So Kolar read Yarek's paper and he tried to understand if there's a way to codify what it is that Yarek needs. And so he says an ideal is MC invariant if it has this property. D of I times this maximal contact ideal is contained in I. So most ideals don't have this property, but the coefficient ideal of anything has, so maybe I should, so coefficient ideal always have this property because they already include all these derivatives with the right. So notice that if this has order A, this has order 1, and this is order A minus 1, together the product has order A. So if there's such a containment, in essence, what this says is that if you apply the coefficient ideal to a coefficient ideal, you don't gain anything because already there's this balancing of the powers. So here's an exercise for you. Show that MC invariant ideals satisfy not just this, but if you put what I wrote here is wrong. di of I times MC to the I. Sorry, this is a, how do you, di of I times MC to the I is contained in I. This is what I need. This is what Yarek needs. The proof I'll give you. So here's Yarek's theorem. Yarek's theorem says that if I have an MC invariant ideal and I have two maximal contact elements, then in a very strong sense, they're equivalent to each other. Then there's a local analytic automorphism of the ambient space, which preserves the ideal and sends the one maximal contact to the other. So if we are looking to have a procedure that is factorial, X prime and X are equivalent. Anything you define using X will be equivalent to anything you define using X prime. That's what this says. Am I presenting it okay? What's missing? Oh, yeah, but I don't need the other automorphisms because you needed it in the old Hironaka method, right? So you needed to know what happens after a sequence of blowups. We don't need a sequence of blowups because we improve things in one step. Yeah, you like to have more, but I know. Any questions about the statement of Yarek's theorem? Or why it is helpful? Okay, so it's incredibly easy to prove this because all you need is to go back to your calculus class and apply calculus. I mean, I use a little bit of algebra here, but mostly I take derivatives, right? So I'd better use calculus. So here I restated the theorem. So this is the statement of a theorem. So the first thing you do is you extend, we are doing things locally analytically, so we extend X and X prime together to a sequence of parameters, X2 through Xn. So I want X comma X2 comma all the way to Xn to be a regular system of parameters, and also X prime X2. So I can always choose parameters that are transverse to both X and X prime. You don't buy this. Okay. Yeah. All right. And I'll just define the stupid local automorphism that sends this point to this point. Of course, the ambient space, there's nothing to say about the ambient space. The ambient space locally is like affine space because it's smooth. So I just choose the stupid automorphism that sends X to X prime. So let's see what happens, however, to elements of the ideal. And remember, I'm assuming the ideal is MC invariant. So let's take an element of the ideal. Oh, I write H for the difference. This is like calculus. H is the difference of two elements, okay? X prime minus X. And I want to see what f of X prime is. What happens when you plug in X prime instead of X in a function? So it's f of X plus H. And I didn't write X2 through Xn. Of course, it also depends on X2 through Xn. F of X plus H times just Taylor expansion. Okay, But what do I have? H is a maximal contact element, is in and this is in D of I. H squared is in MC squared, and this is in D squared of I, etc. So by your exercise was to show that MC to the I times DI of I is contained in I. So the exercise says that each term is in I, so everything is in I. So if F is in I, then if F of X is in I, then so is F of X prime. Oh, sorry. No, that's not. If X is in I, so is F of X prime. So the ideal, and then you reverse the roles of X and X prime because it's it's an automorphism, and you have the ideal is preserved by this automorphism. It's incredible how simple that idea is, but it took 40 years to discover this property. So what he says is that if you want to prove things are functorial, you want to immediately replace I by its maximal contact and proceed from there. At the end, you don't do that. I mean, for computations, you don't do that because going to this raises the degree from A to A factorial, which is crazy. But to prove things, you might as well work with the maximal contact.
Why can you replace
Okay, so this is one of the things. Do I have a discussion of this in my? Yeah, so I will hopefully get to that. How am I doing? Maybe I'll get to that. Yeah, so there's Yevgeny asked, do you go by that name or Jenya or something like that? Okay. So Jenya asked, why can I equally work with maximal contact as with the ideal? Maybe I'll say something about this if I get to it. I think I will, but okay. Okay. My notes tell me to go to page 47, which is rolling slide 98. Let's see if it's 47. Yes. I claimed that the invariant is upper semi-continuous. So first I need to say what I mean by upper semi-continuous. The invariant is a sequence of rational numbers. It starts with the integer, which is the order, and then some order of I of 2 rescaled, and then whatever comes up after that. So I claim that the invariant is upper semi-continuous, and I claim that the process by which we did it, which is it proves it for itself. Okay, so the most pleasant kind of mathematics to do is when the statement prove themselves, and I think you'll agree that this is one of these cases. So I claim that the invariant is upper semi-continuous, and I need to be on page 47 in my notes. Otherwise, I'll lose myself. Okay. So I know that, so this was an exercise for the order, but let me do the exercise for you. The vanishing locus of the ith derivative of I is the set of points where the order is at least I, because if I don't vanish, if the ith derivative does not vanish, this means that I got a unit before, or I mean, yeah, at I or before. So the vanishing loci I closed. So an upper semi-continuous function is a function where the values, where the points where the value is at least something is a closed subset. So that's an upper semi-continuous function. So you have to go back to undergraduate topology to understand this, but okay. Now let's go one step further. We want to understand. We claim say that the maximum order is A1. I want to go through the process of defining the full invariant, not just the order, and see that I will get upper sum continuity. So, and I choose X1 a maximal contact. What does it mean that X1 is a maximal contact? It means that it is an element in, okay, I put the parentheses wrong. Oh. Yeah, that's better. So, except that it will reappear in a minute. Right. So, okay. So X1 is an element of this ideal. So the vanishing locus of X1 contains this locus, contains this subscheme, which is the locus where the order is A. Remember how I formed the maximal, the coefficient ideal. I formed it by putting all the derivative with their respective degrees. So this locus, so here's a little bit, just one reason. So for the purpose of the order, working with the ideal is the same as working with the coefficient ideal, because the order is A if and only if the coefficient ideal has order A factorial. So that's just putting together the definitions. So this equality is an exercise that you can sit down and do. Just see that for each derivative up to the A minus first derivative, you have a correspondence. Okay. Now you restrict to X1, to the vanishing locus of X1. On the vanishing locus of X1, you can apply induction. Remember, the definition of the invariant and the center is recursive. So I restrict to the closed subset, vanishing locus of X1. In that closed subset, the next piece of the invariant is upper semi-continuous. And therefore the invariant, so I have a closed subset on which something is upper semi-continuous. Away from that closed subset, the invariant is definitely drops. So in total, the invariant is upper semi-continuous. Okay. The locus where the invariant is the given one is at least the given one is a closed subset. Does this make sense? Am I? This is, you know, it's hard to go back to undergraduate topology, but okay, we can do it. The same kind of argument will tell us that something a bit more refined. I think I want to go. Yeah, so, okay. Something slightly more refined, which is not quite as much as I need. Which is, so this is just, this just added this one line here. So in positive characteristic, something like this can be done, but you have to be careful and doesn't give you quite as much. The next step will just fail in positive characteristic, but you can define an analog of this invariant. It's just that its properties are not as good. For instance, this will fail in a positive characteristic. In order to know that things improve when I blow up, I need to know that the locus I blow up is it captures all the maximum locus of the invariant. If I don't capture all the maximum, if I don't touch all the maximum locus of the invariant, then there will be points which will remain with the same maximal invariant and will not be improved. So I have to make sure that this holds. I claim that the maximum locus of the invariant is the smallest locus, which is the vanishing locus of the center that I defined for you. Okay, This is something that I need to have. I mean, in this example, I had that the maximum locus was precisely the origin. In this example, where was this? In this example, again, it was the origin, because away from the origin, the invariant is the maximum invariant is 2, 2. So it works in examples, but that's not a proof. So we want to see why this is the case. And again, it sort of proves itself. So I chose a maximal contact element, and everything will have to lie inside the maximal contact, the vanishing locus. So the vanishing locus of X1 contains, this is the same typo I had before, the vanishing locus of dA minus 1 of I. Oh, come on, at least I'll put the parenthesis, the correct parenthesis. And okay. So this is what I wrote before. It's so the vanishing locus of X1 contains the locus where the order of the coefficient ideal is A factorial. Now I'll use the induction of dimension. The induction of dimension says that when I look at I of 2, which is the restriction of the coefficient ideal to the vanishing locus of X1, the maximum locus of the invariant of that is the vanishing locus of the sequence of regular parameters that I chose in the for the invariant for the center, vanishing locus X2 through Xk. If you wish, this is the vanishing locus of a center of I of 2, which lies inside the vanishing locus of X1. This is by induction, by the induction assumption, is smooth. And therefore, I have a smooth locus inside a smooth locus. So V of X1, X2, Xk is the maximum locus of the invariant of I, which is smooth. So this is a point which already in the, so Jarek have a paper where he shows some examples. In particular, the Whitney umbrella in characteristic 2, this fails. You need to do something else. Of course, you know how to resolve surfaces, but this fails in characteristic 2. And you have an example for every characteristic. So this method will not work in characteristic P. You have to make changes, and we sort of know what to do in examples and probably in low dimensions, but we don't know what to do in general. I hope I'm not, maybe you know now how to resolve single, no, okay. This is almost what you need to show in order to know that invariance will drop. You need a little more. So let me show you in the example here what more you need. So remember, what we just showed is that the maximum locus of the, so if this is the vanishing locus of J, maybe I'm allowed to draw on my own picture, right? Maybe in pink. I want thicker lines. The vanishing locus of J is this point here. What I used in this argument that you see here, what I used is that when I look at the entire deformation to the normal cone, the maximum locus of the equations once I clear this is this line here. So J spread out along the affine line. Now, so here's the T line. So this is S. When S equals 0, I have the cone. When S equals 1 or not 0, I have the original variety. So what I just showed you is that the maximum locus here is good. What I need to show is that the maximum locus along here is given by the same center where you plug in X prime all through. Because then when I remove the locus where all the X prime is 0, namely I remove the spread out center, I know that everywhere else that the invariant will be smaller. So this is what I need to show, that the same property that I have here, the maximum locus argument I have here, actually works on the whole deformation to the normal cone. So let's make this argument. Yeah.
J is defined. How is J defined? So J just appeared on this slide, right? The so like smooth locus B of J. And who is J?
J is the center that I defined for you inductively. Is the center I defined for you inductively. Now, I want to tell you that it will work. In order to prove that things improve, I need to show that it's not only the maximum locus here, but also on the whole deformation to the normal cone. So if you look at the arguments in our paper, we didn't write it in terms of deformation to the normal cone because at that point, we didn't know that the Cox construction is the right way to do things. But now so you're getting advanced notice on what will. Actually, Jarek already wrote it in his notes for a book that we wrote. Okay, and here I already said it in positive characteristics. You have to, even in cases where we know how to resolve. I mean, let me put it this way: every singularity you give that you can write in reasonable terms that you give us, we can resolve, but each time we have to think how to. We don't have a process for resolving singularities in characteristic P. That's what we are missing. Okay, so maybe this is another little argument to explain to you why the coefficient ideal is as good as the ideal. So what this in particular, yeah, okay, I'll summarize this in a bit. So I defined the center J, I told you already, it's a Q ideal, but it also corresponds to evaluation, at least locally. So let me define for you the evaluation associated to the center J that I defined for you. So I write a monomial in terms of so maybe I should write J equals x1 to the a1, comma, xk to the ak. And I might as well extend the sequence of parameters. So I have a full regular sequence of parameters at the point that I'm looking. And take any monomial in these parameters. I define the order of that monomial to be by this rule. This is just a monomial valuation associated to the weights 1 over AI. So one thing that is confusing about weighted resolution is that you are all, as we did in the beginning, we wrote x1 to the a1. We had to invert them and rescale in order to actually have the weights. So the weights are really 1 over AI. And I think Jarek in his treatment is always he directly goes to rational numbers. He doesn't worry about integer weights. 1 over AI is the right formulation for weights. Am I presenting it right? So this defines evaluation centered at the generic point or the vanishing locus of J. By definition, if J is the center associated to I, then the order of I, order with respect to this valuation is 1, because A1 over A, did I do it right? Yeah. So the order, yeah. So in the case of x1, what is the order of x1 to the a1? Well, when it's a monomial where only x1 to the a1 appears, then you get 1. X to the a2, only x2 appears, only b2 is a2 and the rest are 0, so you get 1. So this is how the order is defined. And so, okay, so to answer your old question, I don't want red. So the order with respect to J of an ideal equals 1 if and only if the order with respect to J to the power a minus 1 factorial of the coefficient ideal equals 1. So this is another aspect why the coefficient ideal and the ideal are the same. In some sense, the coefficient ideal is a way to blur out the kinks in I, making it a little bit closer to a monomial ideal. So it's the first step in approximating the singularity by a monomial ideal, the last step being J itself. This is, in some sense, the philosophy of Jarek's most recent approach to our weighted algorithm. Okay. Why am I insisting on this? Because this is how I will try to convince you that the maximal locus on the I prime. So I times OB is e to the power L times I prime. So I prime is the transformation, is a transform of I before you remove x1 prime equals x2 prime equals xk prime equals 0, before you remove the center. And I claim that the maximum locus is that spread out center. So the thing that I drew up in this picture. And this is what I need in order to prove that the invariant drops. So let I prime be the transform of I. This is what I wrote here. So how do you calculate? You calculate by plugging in the equations for B. The equations for B are S to the power Wi times xi prime equals x. Xi. Xi. In each function, in each element of the ideal. And I expand F in terms of the order with respect to J. So I think this is something that I had here. I can expand every function in terms of the valuation by homogeneous terms of one for each order Q. So in general, these are rational numbers, but the denominators are bounded. So this is really a copy of the integers rescaled by a certain factor. So doing this expansion, I get that I prime is the leading term plus S times higher order term. So before, if I just plug in, I get a power of S, but this power of S pulls out of the leading term. So S to the power L, this is precisely what I see here, it pulls out of this. And the other terms have an S factor in them. So now let me repeat the previous argument to show that that J written in terms of X prime instead of X is the center, is the maximum locus of the. So this center is the maximum locus of the invariant. So V of X prime is contains the D minus S derivative, because the leading term is already, already has that. So sorry, I'm less focused than I was before, but it's the same argument as before. I accept that here there's something I will need to convince you of here. So I prime is a transform of I. C of I prime is the coefficient of the ideal of the transform of I. What I should have had here is the transform of the coefficient ideal. So there's something I need to prove for you here, that this is equal to this. But once I prove that, you can now continue by induction. So the induction applied to this ideal says that the maximum locus of the invariant of the I prime of 2, the restriction of this to x1 prime equals 0 is x2 prime equal xk prime equals 0 with invariant b2 through bk as before, and therefore the center is the maximum locus. The center J with x primes plugged in is the maximum locus. So it's also, because T does not appear, it's spread out along the A1 direction. Now this is maybe a little technical. There's a technicality that I prepared a proof of here. The technicality is, maybe I'll write it here. Technicality here is that order I prime equals A if and only if order of C of I prime A equals A factorial. What I do know is that this is if and only if the order of C of I A prime equals A factorial, because I and its coefficient ideal are equivalent, and so let's see how this works. This is what I call a hidden computation. What I've really relied on here is that if I rescale the transformed ideal to the power, this power, well, I know that it is contained in the transform of the coefficient ideal and in this, but the claim is that this is contained in this. So maybe in this picture, what this says is that the transform of the, so what I know is that the maximum locus of the invariant on the spread out invariant by upper semi-continuity will include the red part. What the claim is that it does not include anything else. It's still the same locus, that there's nothing sticking out here where the invariant is the same or bigger. So this is what this statement says, and I'll prove it quickly by local computation. How am I doing with time? I'm okay. So I've so this inclusion before I transform, this inclusion implies that when I take when I transform the, well, okay, the power of a transform ideal is the transform power of ideal. So if I transform them, then I get this inclusion. So this is included in this. The hard part is that this is included in this. So I need to show that I take coefficient ideal and I take derivatives and form the coefficient ideal, and then transform is included in the ideal where I first transform and then take coefficient ideal. In terms of maximal vanishing loci. In terms of vanishing loci, I'll have the opposite inclusion, which is exactly what I need. I need that the vanishing locus of this ideal is included in the vanishing locus of this ideal. And for this, all I need to do is the same for the derivatives. So let's work this out. This is page 51, okay? And so there's one secret that I need to tell you. If I is transformed by pulling out s to the power L, then d of I is transformed by pulling out s to the power L minus W1. W1 is the weight of is the weight of x1. It's one here. Wi is the number such that that I get in the denominator in a rescaled invariant. So Wi times Ai is L. So this is the only input that you need in this computation. The rest is calculus. Okay, so we want to show, this is what we want to show. It suffices to show this if I take fewer derivatives here. So instead of taking all derivatives, I ignore the derivative with respect to s. I take only derivative with respect to xi prime. So I plug in xi equals s to the wi xi prime, just as before. What is the transform of I? The transform of I is obtained by plugging in and transforming. Transforming is pulling out s to the L, dividing by s to the L. If I take the derivative of this, so derivative of this, I still can, I mean, I'm taking derivative ignoring s, so I might as well pull that out. Taking derivative with respect to xi is the same as taking derivative with respect to xi prime is taking derivative with xi. So I'm using the chain. Is this the chain rule? The chain rule, yes. Yeah. So I need to multiply s to the wi. So I think this gives me exactly s to the minus L plus s to the wi. On the other hand, the derivative, okay, so this, I just wrote here what we got. The derivative of the transform ideal, this is how much you pull out of each derivative of each generator. D of I is just taking derivative with respect to xi, and if you transform that, you just pull out, you plug in, and you pull out only s to the minus L plus W1. And the one thing you need to remember is that W1 is bigger or equal to the Wi. The W's are basically the inverses of the powers, which means that that I have the inclusion that I wanted. That this, where I pulled W1, well, I pulled L, and okay, so I have a higher power of W1 here than in here, Wi. So higher power of S in here than in here. W1 is higher than Wi in general, and therefore I have this inclusion of ideals, which is exactly what I needed. Okay, so every thing in resolution of singularities requires a computation somewhere. This is a computation that I call it a hidden computation, because in the paper we actually hid it. We referred to another paper, which is what mathematicians like to do. If there's something hard, you refer to, somebody else has worked it out. I have 15 minutes, so I think I told you a lot of things. Okay, so let me look at the list of things here and mark them. Okay, so I made a statement. Let's mark it with. I said something about functoriality. I did not say anything about re-embedding. Did I say something about, yeah, I said something about the independence of the maximal contact and Vodacic's functoriality, upper semi-continuity. This is what you asked for. The maximum locus is V of J. So, okay, so there are two things I can do. Well, there are three things I can do. I can stop right here and ask for questions, or you can ask me to solve one of the exercises, or I can tell you. So one thing I didn't do logarithmic resolution, logarithmic principalization. I wrote notes for that. I don't have to do it. I think it's a neat result that you can use without too much effort, but maybe 15 minutes is a bit tough. So tell me what you want to do. Do you have exercises now? Or? Oh, something about destackification. You insist on that. Yeah, okay, I can do that. So any other requests? Okay. So destackification is, I need to go to slide 42, page. Say again. No. It's harder than that, unfortunately. Okay. So so what's here is just a hint, and I can tell you more. I have 15 minutes, so I can probably tell you more. Okay, so stack theoretic weighted blobs give us stacks, not schemes. So we start with a scheme. We want to resolve it by a scheme. And I told you, I insisted all these 3 hours that, oh, it's okay to have a stack. But, you know, you're all birational geometers, you want a scheme. So what's the story? So, okay, so I'm here. Okay, so let me draw a picture. So we start with a scheme. So with a scheme that I want to resolve, and I gave you a stack X prime, which is smooth, which resolves X. In Yarek's terminology, Yarek would give you a variety on which a torus acts, such that the quotient has a proper birational map to X. So it's a resolution up to quotient singularities, if you wish. So one thing you can always do, this is Keel and Mori, is take the coarse moduli space. I'll write it as X prime underline. That's another scheme. Maybe I'll move this a bit lower. Okay, so by functoriality of course moduli space, there exists a map like this. Okay, exists a unique map like this. So X underline prime, that's a scheme. It is the coarse moduli space of a smooth stack, smooth Deligne-Mumford stack in characteristic 0, but there's no reason we should believe that it should be smooth. In general, it's not. So if you take A2, a model of the involution that flips X and Y, we get A1 singularity. That's the first singularity we love as birational geometers, right? So this is singular. But in all the process that I'm doing, I'm taking a, I'm taking a C star variety and I'm modding out by the C star, and then taking a C star variety. So in all the process, I'm adding a torus, and so the stabilizer of any point on the stack will be subgroups of a torus. Subgroups of a torus, which are finite because this is a Deligne-Mumford stack, are abelian, because a torus is abelian. So this is a scheme with abelian quotient singularities. So for some times I was convinced that that I discovered this trick first, but I was shown. I mean, Yuri Chinkel has for years shown me that every good idea I had, Fedya Bogomolov had 10 years before. So, so Bogomolov in particular, so I had something about the resolution of quotient singularities. Bogomolov showed how to resolve easily varieties with quotient singularities. And other people also did that. And Jarek showed how to resolve quotient singularities, especially abelian quotient singularities, easily. So one thing you can do is say, well, these are singularities that I don't really worry about because I know how to resolve them. I'll put a tilde for the resolution. So here's your resolution because you pull out another mechanism for resolution. Some people think that this is cheating. So here's another, it's cheating because it's not really using what I have. So another process which in particular enables you to prove wonderful results about stacks is called destackification. So you can always do the following. So this is Berg's destackification. Suppose you have a Deligne-Mumford stack in characteristic 0, or more generally a tame stack with finite diagonal. Then there exists a sequence of blowups and root constructions, so a sequence of stacky blowups. That is combinatorial, easily described. So each time you blow up a smooth center, or you take a root construction and log a smooth divisor. So this is. So that, of course, you start, so this was already smooth. So this will remain smooth. But the additional property that it has is that its coarse moduli space is automatically smooth. So Berg's destackification has this property. So let's look at this example. So, okay, so this example, we know how to do it both on the coarse moduli space. So, and above. So this is an example where the stack has an easy destackification. So let's write it this way. Come on. If I blow up the origin on A2, I still have an action of plus or minus 1 on it. And the beautiful thing is that in this case, the coarse moduli space is smooth. And it is actually the blow up of at the origin of this. So what Berg says is that you can always do it, but in order to do it, you need to blow up and also sometimes change the stack structure. So this is what I'm saying here when performing the. Okay, so this is what I already said, what Kilmore says. Destackification in a particular way. So here's an example. So assume in general mu n acts on A2 diagonally, then you just blow up the origin on A2 and the coarse moduli space is smooth. So that's the easy case, but the harder case is when you don't act diagonally with the same weight but with different weights. you still know. So Berg tells us how to do it.
But this process itself is not relying on low resolution of the inertial.
It does not rely on Hironaka resolution. No, it's a combinatorial process. It's so combinatorial that I had a group of undergraduates code it for me. So it's, yeah, you can do it. No, the Kirwan resolution is in the case where you have higher dimensional stabilizers. So I don't know an analogy. So what I know is that you can, this is just for the Lin-Mumford stacks, but Edidin and Reed have a Kirwan resolution for Artin type resolution for Artin stacks, which enables you to, for good Artin stacks, namely those that have good moduli spaces, you can do this process. You can extend the destackification process so that you reduce the dimension of the stabilizers before you do baric destackification. So you can combine Kirwan and this. Does this sort of answers your wishes? I have 5 more minutes. I don't think I can say much more about destackification. I can say something about anything you ask me now. Let's resolve characteristics in positive characteristics in 5 minutes. So let's take x to the p equals y to the pz. This is an example due to this gentleman here. Okay, what's the worst singularity? Worst singularity, oops, what happened? Is the origin. It's clearly the origin. And the same process that we, of course, P is the characteristic. So P is no longer a point now because P is the characteristic. Of course, the origin is the worst point with invariant P, P plus 1, P plus 1. And you want to blow up x to the P, y to the P plus 1, z to the P plus 1. And let's do it and see that we are stuck, and then we understand why. So, of course, you have to rescale it. So rescaling it x to 1 over P plus 1, y to 1 over P, y to the 1, z to the 1 over P. That's the, so this means that I need to plug in x equals s to the P plus 1 x prime, y equals s to the P y prime, and z equals s to the P z prime. I plug that in, and I get, okay, so I'll change it to an equation. I plug that in, and I get s to the P plus 1, x prime to the P minus y prime to the P z prime. This is exceptional. Okay, so I thought I got rid of the worst singular point, but I did not. Why is it that I did not get rid of the worst singular point? Because every point on the handle of the Whitney umbrella in characteristic P has the same singularity. They are all, the handle is equisingular. This is worse than the umbrella that couldn't save us from this rain. It's an umbrella that could not do any good. Okay, so why is that? So in the homogeneous case, you have this wonderful situation that so look at the following family of automorphisms of this equation. So x, y, z. So the family parameterizing by parameter t, x plus ty, y. I hope I did it right. So x to the p is transformed to x plus ty to the p, which in characteristic p is x to the p plus t to the p, y to the p. And y to the p z is transformed to y to the p z plus t to the p, which is y to the p z plus t to the p y to the p. So x to the p minus y to the p z is transformed to x to the p minus y to the pz. So the ideal is preserved by this one parameter group of automorphisms. What does this one parameter group do? So, okay, away from the z-axis is sort of rotates, but on the z-axis, where x and y are 0, it doesn't change x and y. It just very, very slowly goes along the z-axis. It goes by the Frobenius of the affine line. So this is an action of the affine of the additive group, and it's very slow. Through Frobenius acts along the z-axis. Very, very slow, but it still moves. Every point there is the same as every other point. Also, in some sense, the generic point is the same, because if you look at the geometric generic point, it has the same invariance. So somehow all the points are as bad along the z-axis. So what happened here is you remove the locus where x prime equals y prime equals z prime equals 0, but you left the rest of the equisingular locus untouched. And if you leave things untouched, you have no chance of improving things. So what do you do to resolve this? Of course, you resolve it by blowing up the whole. So the correct thing is to blow up x to the p comma y to the p and ignore the z. Z somehow. So you have to do something that is invariant under the group action. So in this case, we know what to do in general. You think that you know what to do in several examples, and Jarek will give you a counterexample for each guess that you have. So any idea that you have to first ask Jarek to give you a counterexample. Okay, I think I'm done.
The x prime theta underline is theta. Yeah. So for the birational geometry,
This is nice, yeah. Yeah, Q, yeah, it's Kel, yeah. Yeah. You don't need anything, but you know, when you start doing, I mean, you talk to people who need to work with D modules or with yeah. If you want to work with if you want to work with, you know, if you want integer, if you want it's log terminal. So yes. Is the underlying, is the old-fashioned weighted blow-up. It's a singular weighted blow-up, yes. So the only difference from the way what we have done and the old way of thinking is that in the old way of thinking, people accepted that, you know, this is singular, but maybe not too bad. So for Birational, I mean, you use weighted blow-ups because they are not too bad for birational geometry. You can do a lot of things with them, but there are still techniques that don't work, right? You want the integer cohomology ring? Good luck. The stack will give it to you.
this way go up.
So locally, you need the system of, what is the global structure? That How do you patch things up? This is an interesting story. So what is J? Oops. So there are various ways of thinking about it. So J is a Q ideal, or we call it valuative Q ideal. Sorry. So what do I mean by that? Or Hironaka's terminology, it's basically equivalent, is idealistic exponent. But not, so he has a very wide equivalence, so not up to equivalence, just the idealistic exponent. What is that? So an idealistic exponent is an ideal I with an integer d, which you think about as I to the 1 over d. Okay, and so you need to think of the, so I1 d1 is equivalent to I2 d2 if and only if I1 to the d2 I2 to the d1. So idealistic exponent only work nicely on normal varieties, and you always take integral closure. So idealistic exponent is an equivalence class of pairs ideal, comma, and integer, where you think about them as fractional powers of ideals up to integral closure. So you can always rescale by okay, so what do I mean by x to the a1 through, or x to the 1 over w1 through x to the 1 over wk? What I mean is the thing that when you rescale, you take this ideal and you put the L here, and that's okay. So how do you work with this? So you can form ideals IK, which is the so IK is J to the power K intersected with OY. So J to the power K is a fractional, is a Q ideal, and you take just the function that lie in there. So and right. So the information that so this is a what do you call this? A filtration, an idealistic filtration. What does Lazarsfeld call this? Is a sequence of ideals such that I to the K, I to the L is contained in I to the K plus L, etc. And you can, if the corresponding algebra is finitely generated, you can form its stack theoretic proj, and that's what we do. Who asked this question? I forget. Okay. Have I answered your question, Jania? So AI, my AI were so J was not an ideal. J was a thing with fractional powers. You raise it to a power so that all the AI become integers, and you put the power as a fractional power that you use in. So it's a smooth subscheme with a Riesz algebra. So what these form together form a Riesz algebra, a finitely generated algebra of ideals. So it's something that you can take its spec, you can take its proj. So it's that. So one thing you need to know is that such a center, the right thing to have is not so the center is smooth in our discussion. You can define it more generally, just like with blowups of ideals. You can define it more general, but we are interested in the case of a smooth center. Its normal bundle is not the right thing to take. So you don't take the deformation to the normal bundle. You take the deformation to the weighted normal bundle. And a weighted normal bundle is something new. It's not a vector bundle. It's a GM affine bundle. It's an affine bundle with an action of GM with a section. And so the gluing maps are nonlinear. So when you, yeah, so it's an interesting gadget on its own. And I should point you again to the paper of Queck and Reed. That, as I said in the first lecture, appears, so the only place to find it yet is on David Reed's webpage. It has been there slowly, adding one last section each time because David Reed wants to be perfect. Have everything there, but what you need for my lecture has been there for 3 years.
Okay, and any more questions?
Okay. How about classical Kernel? Can you deduce it from your?
So in Hironaka's classical algorithm, okay, so the question maybe has two parts. Hironaka achieves more. Hironaka achieves logarithmic resolution. And in my notes, I have, in essence, a deduction from what we did with a little bit functoriality and thinking. We deduced logarithmic resolution as well. So we can recover something equivalent to Hironaka's theorem. The other question is, can we recover something more like Hironaka's original algorithm, which works in a different way? And my answer is a lot of the elements are the same, but what we do is different. So, and I'm not convinced that I want to recover Hironaka's original algorithm, because Hironaka's original algorithm has to fight with the fact that the first example that I gave you, maybe I can go back to that first example. That okay. Oh, so that's okay. So you want to replace a sequence of weighted blowups by a sequence of blowups. So now I understand what you're asking. We have not tried to do that. So, we've written papers using Hironaka's original methods to prove things that are related. So, I mean, I've learned Hironaka, I know how to do it, but I see your point. Yes, if you want to use usual blowups, then this algorithm does not directly give it to you. You can ask, why do I want usual blowups? One reason is to have factorization of birational maps, for instance. And why do you use usual blowups? The reason usual blowups are so desirable is that you know exactly what happens to the geometry when you do a usual blowup. But the truth is, you also know what happened to the geometry when you do a weighted blowup. In my lecture in a few days, I will tell you how to calculate. So Fulton tells you how to calculate the Chow ring of a blowup. I'll tell you how to calculate the Chow ring of a weighted blowup. And when you do that, you actually learn something about the usual blowup. You learn something new about the usual blowup. So I think it's worthwhile. But I see your point. If you want to have blowups, then Villamayor, Birston Millman, Wodachik have given you Hironaka style algorithms, and we are not, the weighted algorithm does not recover that.
Hey, yeah, thank you very much. So let's thank Dan again for the very wonderful lectures.